Welcome back. In this video we're going to go over another example problem, this time with a voltage divider that has 4 plus elements in it. In our case, we're going to be looking at a circuit that has 4 resistors in it of all different values. And the goal is to determine the voltage across each of them individually. So to get started, let's just look at Ohm's law for the resistor 2. Now to find this, we're going to need to look at all of them combined. The voltage source is equal to all of our loads combined. And substituting in Ohm's law, we get the following equation. Now, since the currents for each of them is the same for the loop, we can just substitute the current for all of them, then factor that out, and notice we've got an equivalent resistance here, which is an Ohm's law case. So our equivalent is equal to all 4 of these resistors added together. So let's hold on to that for a second. Now, notice I can move things around so that way I have current, and now we've got the current and the resistance. So plugging in all of these together, we get the equation for the voltage across resistor 2. And this is the exact same derivation for all 4 of these resistors. So what we can do now is we can determine the voltage for each resistor individually and plug in the numbers. What you'll find is that we get the following voltage values for each one. Notice, more resistance equates to more voltage. Now, if we multiply it by current, we could get power. Again, same current for each of them. And we already know the current. It's 1.71 milliamps. So, multiplying these together, we get the power draw for each one. And notice, more resistance equals more power drawn. Alright, so I hooked up our circuit with each of the values that we calculated. And what we're going to try and do is measure how close we can get. Now you'll notice that the power supply I'm using is a little bit off from what I'm measuring, so that might affect our measurement a little bit. So what we're going to do is measure the voltage across each resistor. So this is pretty close to what we calculated. That's also pretty close to what we calculated for the 330 ohm resistor. For our 3, we're basically within rounding error. And we're also pretty close for our 4. Now let's measure the current, and if this is the same voltage and current for each of these, we've also done a good job at determining how much power we're probably going to be using in the circuit. Okay, I hooked up the current to see how much current we're measuring, and we see that we have 1.71 milliamps, exactly what we calculated. So as you can see, for the voltage divider with resistors, our theory is very accurate to what we are measuring in reality. So we saw that that worked out pretty well in measurement. We actually derived these equations in general. So in general, for n resistors, we can go around the loop and the voltage source is equal to all the elements combined. And plug in Ohm's law, factor out current, and we have our equivalent resistance here for every single one of these resistors in series, which is the equivalent resistance is equal to all of them added together. In shorthand, we could use summation notation. So resistors in series, you just add them together to get the equivalent resistance. And we have the voltage source is equal to our equivalent times I source. Now to find the voltage for any of them, let's look at the Ohm's law for that one. We can plug in the same currents because this current is the same throughout the loop. We can only do this because the current for every single one of our elements is the same. So, solving for current, we can put these together, and then we could solve for the voltage for one of those resistors. And then this gives us the general equation for any resistor's voltage. However, it's good to know when this equation is accurate and what assumptions we made. The big assumption that we made here is that the current was the same for each element in our loop. And this equation will work as long as the current is the same for each of your components. But when is this not true? Well, if we were to add in a line out of here, out of our circuit, to another circuit, for example, a current out, now this is no longer true. The current going through the loop has to divide to the output current and to our resistors on the bottom half. So the currents between all 4 resistors is no longer the same. However, you could still use this equation for these top 2 resistors using the voltage source of VR1 plus the voltage for R2 And you could also use this equation separately for the bottom two resistors, but in this case the voltage source would be for the voltages of R3 and R4 combined. Let me know in the comments below if there is another example you'd like to see, and I might make a video about it. In any case, I'll see you in the next video.